recording. Okay, good. Um, okay, hi. I think I might have met a couple of you before in the Math Lounge or something this year. But if you don't know me, my name is Adam. I graduated spring 21, and I work at Facebook now, so I'm not really doing anything math related. But I do like math a lot, and teaching is fun, so here I am. So someone messaged me uh earlier asking why I'm doing this. And I need to reveal to everyone that this is actually a bait and switch. So let me share my screen. Um, oh, can I not share audio if I share a window? Okay, right. It turns out it's really hard to tell people that they put Among Us in Fortnite. So I made this server just to share this with you guys.
We've run things successfully for thousands of years. We, the imagined order, facing crisis after crisis without a single failure. But since Jones betrayed us, now it's clear. He wasn't working alone.
Okay, so I hope everyone enjoyed that except for the one person who just joined. Um, so I like having the server having a theme, and yeah, they did they did put Among Us in Fortnite. I've actually played this, and it's surprisingly well made. But anyway, stupid things aside, I like to make sure about half the things I say are nonsense, so take everything I say with a grain of salt. Um, so we'll get to the lecture in a moment, but I have some amount of forward to just talk about real quick. Okay. So, uh, the name of the course at Rutgers is Introduction to Mathematical Reasoning, something like that. Um, so, the actual goal of this course is not to learn how to write a proof, and the reason for that is simple. Writing a proof is really, really, really hard. The goal of this course is to learn what constitutes a proof. So being able to look at a supposed proof and determine if it's valid or not. Um, and this by itself is also very difficult. It's just an entirely new style of thinking. We're used to making a lot of jumps in our logic, making a lot of assumptions, and all of a sudden we have to go back to very simple things that we're just assuming and start proving them. So this is just very difficult and it takes a lot of time. So roughly the structure of this course is uh, roughly the structure of this course is the first four lectures are like a tutorial, I guess. So you'll learn like basic logic, sets, um, uh, and basic proof techniques. And then once we get to lecture five, then we're gonna start doing we're gonna do a kind of structure where I give you some kind of object. So maybe I define a graph for you, or I define a group, and then I'll say, okay, write a bunch of proofs. So the more proofs you write, the better you will get at understanding what constitutes a proof or not. And throughout this process, something really critical is that the graders will be giving you feedback on all of your proofs. And this is really, really key. So someone mentioned, I see a lot of cameras turning on. I appreciate that. Um, Someone mentioned to me elsewhere that they had read some kind of proof book, and I saw the content. It was pretty much most of the content that you would see in 300. Um, but what's missing from just reading a book is when you actually go to write a proof, how do you know that the proof you're writing is, actually a proof? So that is going to be a really big part of this. Um, so I have in my notes, I should explain what is a proof, and then I didn't like write anything, so let me ad lib here. So, uh, so when we talk about a proof, right, you might be thinking like, okay, we have some explanation for why something is true, but what actually makes it valid? So, I mean, you could write a really, really verbose proof where you write all the logic just axiomatically, and it's definitely correct, but it's just not readable, right? So you couldn't ever write a paper like this. It would be impossible. It'd take too much time. So how do you know when you should, skip a step or something like that? And figuring that out is really hard. Just the style of writing is really difficult. So that goes into proofwriting. Okay. So when do you actually learn how to write a proof properly? This just happens in later courses. So 300 is the starting point. Later on, you would take 311 or 351, which would be analysis or abstract algebra. I'm getting a ping here. Okay, that's not relevant. Um, and then you would take like maybe honors track courses like 411, the honors analysis, 451, honors abstract algebra, so on and so forth. And I think, by the time you finish the honors track, you can say you know how to write a proof pretty well. Okay. Um, Now more comments about the course. This is going to be really hard. So by nature, this is a new style of thinking, so it's just hard by default. We're also doing this over the winter. So we're going to have, 3 lectures a week. It's going to be very fast paced. You're going to be having a lot of homework. But it's absolutely necessary to do this much work to understand it. Um, so that being said, we're really fortunate. We had 7 people sign up to be graders, and there's also me to help out. And we're all here because we just want to help you guys learn math. Because math is fun. So if you're ever feeling lost or confused, like please just ask questions. Ask in DM to a grader. Ask in the general chat or whatever, and we're definitely gonna help you guys out. So I mean, it's gonna be a different environment from like a Rutgers class because the professor is gonna be kind of detached. You have to send an email or something like that. But we want to have like a really open communication here. Okay. So flipped classroom. So this is a really interesting thing. I'm kind of just doing it to like save time, but if you've heard of this before, the idea is before you go to class, you do all the preparation so that when you actually go to class, you don't have to waste any time doing thinking you could have done by yourself. Class time is just full of things that really require you to be talking to the professor or your classmates directly. So the plan here is before every lecture, spend about 1 hour going through the notes. It could be less, but I think 1 hour is roughly a good benchmark. Um, and just understand the definitions at least, and have a good think about the problems. And that will leave you in pretty good shape to make the lecture quite parsable. And I am gonna be lecturing pretty fast. So I think the first lecture is like this lecture right now. It's the equivalent of like the first 4 lectures in Math 300. I don't know how that's possible because I didn't think it was that fast, but I mean, clearly it is fast. So you do kind of need to do a little bit of prep in general to keep up. Okay. Any questions so far? There's only one question in chat. The answer is yes.
So was there a reading for today's lecture? It's like I
Yes.
was like on a plane for the entirety of last night, and so like I couldn't do
That's
that.
okay. That's okay. So, yeah, like, okay, so maybe I scared you by saying this is the equivalent of 4 lectures, but so okay, let me share my screen because it's not as scary as it sounds. Um, um, so these are the lecture notes for today. Um, it's literally just 2 pages, and the rest is homework. So this is actually really not that bad. So I think you'll be fine just sitting in, especially if you're 291 student and you're doing okay. I don't expect you'll have any trouble at all following on this lecture. If you do have any questions, obviously feel free to ask, or you can ask afterwards. You can DM me, whatever you want. You should be fine. Any other questions? No? Okay. Let's continue. Roughly 3 more points to get through. So LaTeX. So for example, this PDF was generated in LaTeX, with like LaTeX rather. So it's a way of just formatting math nicely on a PDF. You can do some really crazy things with it. But obviously, this kind of thing, you basically just need to understand like how to write certain things. So for example, here I'll explain like if you want to write this symbol, then you would use this command in LaTeX. So If you're submitting homework, it has to be in LaTeX. The reason is because the first time we did this, we had people submitting like pictures of like handwritten stuff, and it was like impossible to read their handwriting sometimes. It just makes our lives a lot easier to do in LaTeX, and you need to learn LaTeX anyways to do math. So, um, you will be learning LaTeX. If you haven't played with it before, go to overleaf.com. That's this website here that I'm on right now. Make an account, and you can basically just copy my template from the lecture notes, paste it in, and then start modifying whatever is here to format your problems. And you can Google stuff and figure it out, and it shouldn't be too hard. And of course, with LaTeX, you can just ask us questions too. Okay. So grades. So yeah, the last 2 years, I was paying attention to grades because um, I had to give some kind of recommendation to the math department if a student doing this should skip 300 or not. But now the math department has taken away this possibility, so grades literally don't mean anything. Um, but that being said, please don't share grades. And more generally, I think we should just try to be cognizant in general of, whether we say something is easy or hard, or no, just easy. So I would like to avoid situations where people think, okay, this is easy, this took me a short amount of time, and then someone else is struggling because this is a hard course, and they just feel demotivated. So don't share grades; they can make people feel bad. Don't make disparaging comments. And other than that, yeah, one more point about collaboration. So again, so grades don't matter. So this is an interesting thing now. So I was debating if I should let you guys even just make groups and submit as a group, but I think this pretty much just defeats the purpose of the way I've structured the course, because there's a lot of merit to doing sort of the mapping from logic to language. Um, so if you have a group submission, then there's obviously going to be a lot of things that you didn't write yourself. So you're not doing the important part there. So you can collaborate, like figure out the logic together, problem solve together. That's totally fine. Feel free to do it in general, make your own group DMs, whatever. But what you submit, if you want a grader to actually give you feedback on it, make sure that it's like something you wrote. Um, or if you don't feel like writing it, then you could also just ignore it. But like just just submit your own thing as frequently as you can, and that's gonna help you as much as possible. Okay. That is everything I wanted to get through. That took about 10 minutes, so we're on time. Any more questions about the structure of the course or logistic stuff, whatever? No? Okay. All right. Let's get started then. So, yeah, I have a short forward here. So I think the biggest thing I want you to keep in your mind is that, you're really used to making assumptions like all over the place. And when I was learning logic, I had to really like beat it into my head that I need to stop just making assumptions, just writing statements down that I want to be true because I'm trying to solve the problem, and instead really, really analyze things atomically. And when I say atomically, I mean like every single logical statement should be backed up properly. And then once you do it truly atomically, then you can start learning how to skip things slowly, and that will come more later. Okay. Blah blah blah. Spend time. Okay. First lecture, formally speaking. Okay, so here's our first definition: a proposition. So it's a statement which is either true or false. So here are some examples. I'm a dog. Uh, this is false, thankfully. Sometimes there are clouds in the sky. This is true. I'm sure some of us have seen clouds in the sky. The Riemann hypothesis is true. So I don't know if this is true. I don't know if it's false, but I know it's one of the two. So this is also a proposition. These are non-examples, and actually these are really bad non-examples because these are just nonsense. And the reason these are bad is because it's actually kind of hard to say statements that are like neither true nor false. So yeah, this is your first definition. And whenever you see a definition, so did any of you guys come to Ruma's Q&A panel earlier this semester? I'm getting no's. Okay. So Professor Beals was there, and he said something really nice about how. Okay, we have one yes, good. He said something really nice about how when you learn math, you're kind of uh, building the entire world of mathematics again for yourself in your own head. And I thought that was a really beautiful way of putting it because, like, by learning math, you're constructing this really intricate web. Um, so, anyways, when you're constructing this web of knowledge, this is something you almost always want to do when you see a definition. You want to make a non-trivial example and a non-trivial non-example. And the point of this is that it will help you differentiate uh, when the object is useful or not. So here we see examples and non-examples, and the examples show us that okay, propositions talk about like facts basically, and something's not a proposition if it's not something I can really talk about in a factual sense. Okay. Boolean functions. Um, could you can we try something? Can you press the raise hand button on Google Meets if you are a CS major? Okay, I didn't finish my sentence, but okay, we have four raised hands. Five? Okay, great. So, um, Paul is Homo sapien. True. This is a proposition. I think it's also a true statement. Okay, so you can put your fake hands down. Um, so yeah, if you are a CS major, the Boolean function should be very obvious to you. But we'll tackle it anyways. Um, so there's a nice word here, truthiness. It just refers to whether something or the state of something being true or false. Um, so it's a function. It takes in something, and it outputs something. So in this case, we have a Boolean function d. It takes in x, and it returns the truth value of x is a dog. So d of x is basically just telling you whether or not x is a dog, right? Um, Pretty straightforward. L of x is defined as x loves dogs, and f of xy is true exactly when x considers y a friend. So it can take in any number of variables. I guess it could technically take in no variables too, but don't do that. That's weird. Um, okay, so we have Boolean functions. Okay, and so here we have this walrus operator here. Walrus because if you turn it sideways, it looks like a walrus. Um, so it's kind of a nice way to show the reader that you're defining something explicitly. You could just use a regular equal sign, that's fine, but walrus is nice. Okay, so conjunction. So again, if you're a nice CS major, this is very obvious to you. This is logical and. So this is a way to combine two propositions together. Um, and we also have disjunction, logical or. So obviously, if you have a conjunction between two variables, two propositions, rather, I should say at this point, um, then the conjunction is true only if both individual statements are true. And for logical or, the disjunction is true only if at least one of the two propositions is true. And this follows our intuition, so I'm not going to go more into that. Okay, so yeah, we have some LaTeX here. So I think as frequently as I could, whenever I introduce a new symbol in LaTeX, I have the command next to it. So if you're ever trying to write LaTeX for your homework, looking over the lecture notes should probably help you if you're missing a symbol. You can also just Google like how to write LaTeX for a certain symbol, and there's also a website called Detectify. Now that I remember, Detectify. So it's like if you like machine learning, it will classify. Okay, none of these are what I wanted, but you get the point. It will classify this and tell you the command to use. Um, don't use these. So um, okay, we have some machine learning levers. Let me just put this inside of something. In that. Okay, so that is saved for you guys. Okay. Right. So this is an annoying thing about English. Um, so I write tends to, not always. But there is this kind of implication sometimes in English that when I say or, I mean exclusive or. So if someone said get me a spoon or a fork, presumably they're trying to eat something, and they don't want both because that would be a hassle. So, uh, Big data. That's terrible. Yeah, this chat is hmm. Anyways, so in logic, we always mean the not exclusive or, so you can have both things true as well. Okay. Um, so these are powerful, blah 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 blah. Okay, so here's a nice Boolean function. So g of x, y, so we're defining something here. So let's go to our old definitions. L of x is x loves dogs. And f of xy is the friend function. X considers y a friend. So g of xy is defined as uh, x loves dogs and y loves dogs, and x is a friend of y, and y is a friend of x. So just in plain English, g is a function that tells me two people are dog lovers and also friends. Okay. So I mean, this, I guess it's kind of powerful. It's not super interesting, I guess, but we formed a relatively complex idea using just conjunction. Okay, so now we're going to talk about sets, but like in the fake sense. And let me just check. Okay, so I don't actually talk about it too well. So next lecture, we will talk about sets properly. Here, I'm going to talk about sets, but you should just pretend for now that they're just a collection of elements and nothing more than that. Okay, so we have this upside down A. So in LaTeX, we have this backslash for all, and it's known as the universal quantifier. So a quantifier is saying that something is true in the context of something else. Universal means it's true for everything. So there's only ever one way to use this universal quantifier in sort of a logically sound sentence. You would say for all elements x in a set, capital X, f of x is true. So you would never really break this format. So I do see sometimes a little bit of confusion over how to use it. But as long as your statements always look basically exactly like this, then you're probably not using it wrong. Okay. Um, and the shorthand, or just like the way to write it out in logic, is like this. And here's the LaTeX. Um, so again, here's the upside down A. Here's the containment symbol. So this is saying that x, little x, belongs to capital X. And then as a result of instantiating, we call this instantiation of a variable. We have this little x to work with now. So after doing that, now we can talk about it, and we say capital F of x is true. Okay. However, I am telling you how to write the shorthand here, but in general, when you're writing a proof, you're not going to be writing the shorthand stuff. The reason is simple. It's not very easy to read, and you want your statements to flow like English very nicely. So in actual papers, you'll basically never really see this kind of language. Um, so do try to avoid that in your homework. But if you want to write, some scratch notes, then you probably want to do something like that. Okay. Um, so we have an English statement. Blah blah blah. Bob considers everyone in his class a friend. So this is a sort of universal statement. So we intuitively we identify he's talking about everyone in his class. So we have a set of people, everyone in his class, and we have a statement that would be true for each person in that class. Bob considers them a friend. So yeah, so let's define some variables. X will be Bob. Capital C will be Bob's class, and we're going to use the friend function from before. So then what we would write is simply for all y in the set C, f of xy. Okay, so I've said many things. Are there any questions as to why this corresponds directly to this English statement? No? Okay, good. Let's move along then. So we have a sort of counterpart to the universal quantifier. It's the existential quantifier. And just like the universal quantifier, there's only one way to use it. I basically copy and pasted the same thing from above. And instead of talking about for all elements in a set, it's saying there's at least one. There's at least one element, little x, in a set capital X, such that capital F of x is true. And the shorthand is, of course, very similar. We have a backwards e here, and that is going to be backslash exists. Okay, so let's try using it out. So among all animals on Earth, at least one is a dog. So we think of what set we have. It's going to be all animals on Earth. We think of the proposition. The animal in question is a dog. And then we see that we're talking about at least one. So we're going to use the existential quantifier. So great, we have the set. And then we have just this sentence. Or rather, this shorthand. There exists x in A such that d of x is true. And yes, we have a note here. This colon is read as such that. Okay, everything fine and dandy? You can hit the raise hand button if you have a question. No? Okay, good. Everyone's doing great. How are we doing on time? Okay, we're only half an hour in, so we're gonna be done pretty soon. Good. Okay. So I'm gonna point out that a Boolean function itself can make use of quantifiers. So let me just clarify a little bit. So we had a Boolean function before. D of x is defined as x is a dog. And I can use these Boolean functions, for example, when using for all, right? So here I'm using a Boolean function. But this Boolean function can in turn refer to another Boolean function. So we have a recursive structure here for you computer science majors. And for anyone who may have studied it, there's a grammar that describes this. And the math that's involved in the grammar of logic is really, really interesting. But I'm assuming you guys are mostly freshmen or sophomores and haven't seen that yet. Anyways, oh, these are spoilers. Okay, so I've taken away the thing, and hopefully no one will cheat. So I will let's do this. Don't look at the title. Much better. Okay. Okay, so here is the first statement. It thinks this is what is J? Does anyone know what J is? VS Code thinks this is Julia. That's interesting. Okay. Anyways, who wants to try converting this statement into logic? And so, in order to do this, you're gonna have to make use of some variables from before. So in particular, I think the only one we really need is we just need C is defined as does anyone want to take a stab at this? And just hit the raise hand button, or you can type in chat if you feel like it. No takers? So this one is harder because this involves. Oh, we have our hand raised. Okay, Paul, go ahead.
I was gonna say, can we use the Boolean function, like the f of x comma y?
Oh yeah, sorry, you do need that.
Okay.
My bad.
Okay, that makes it easier.
X considers y. Yeah, I would agree that makes this easier.
Yes. So you could say there exists x in C. Such that f. Oh wait. You could also say actually before that you could say for all y in C.
So here.
Yeah. Yeah, so for all y in C, there exists x in C such that f of x comma y is true.
And so we have a second answer in chat. So what's the difference between these two? Well, it's pretty obvious when you look at it, right? It's the order. So one of these is right, one of these is wrong, and let's think about it very carefully. So in the first one, we say for everyone in the class, there is some person in the class such that X considers them a friend. So this is actually wrong. And the reason is because, let's say, I see some interesting reactions on the video cameras. Anyways, we can you guys are having a lot of fun. Okay, so here's the counterexample, right? So let's say C is equal to just two people. Let's just call them 1 and 2. So 1 considers 2 a friend, and 2 considers 1 a friend, and 1 doesn't consider 1 a friend, and the same for 2. Okay, so they're between 1 and 2, neither of them consider everyone in the class a friend, which is what we needed here. However, in this situation, we actually satisfy this other thing here. So for all Y and C, there is someone who likes them. So if we pick 1, then 1 is considered a friend by 2. And if we pick 2, then 2 is considered a friend by 1. So we can see that this is actually a different statement. And if we look here, what this is saying is there's some X in C such that X likes everyone in the class. And it's really just the order. So for your CS majors, you can literally just think of this as like for loops, right? And the difference is that whatever in the second, whatever 2 actually can depend on X. In this case, it's just the class again. But the point here is that X is now in the scope, right? X is now a thing that matters. But when I go to the next Y, that X is sort of that X is the same. So yeah, so keeping track of your variables is a little tricky. But I'm actually really glad that we saw this example really early on because this is something that trips people up a lot. Okay. So let's look at the next statement. There's a person in the class who everyone considers to be a friend. So give that a moment, let that chug. And who can tell me how to write the logic for this? Will I post the notes later? Well, the notes are already posted. The big O is n squared, although you've written big parentheses 0 for some reason. Yes, nested for loops usually give you quadratic runtime. By the way, if you're confused as to where the notes are, look in the Tomato Town channel and look at the pin messages, and that has like the important stuff. Okay, any thoughts on this question? Okay, I'm blankly staring at people. I feel like people do know the answer, so I'm just gonna start writing. So let me tell you at least my thought process for this. So there is a person in the class, so I immediately start thinking, there exists X in C. And then I know that when we write in English like who here, then the rest is kind of scoped in terms of this person. So I know that this variable is going to go first. And then I see everyone considers to be a friend. So I see everyone and I say, okay, such that for all Y in C, and then each person considers them a friend. So I know that Y considers X to be a friend. So it's actually pretty much the same thing as before, except this thing is reversed now. Okay, let's move along. Everyone has at least one person they consider a friend. Does anyone want to try this? If you feel like that you know the answer, just feel free to type it out. Okay, we have some guesses. They are identical. Good. At least we have some consistency. And let's examine. So, okay, I agree with how it starts. So when we say everyone has, right? Then I kind of scope it like this. We're making a statement about everyone. So it makes total sense to me to start off by saying for all X and C, and then we say at least one person. So then, so we're talking about at least one person in the class. So yeah, I would immediately write exists Y and C, and they consider a friend. So then I would write it like this. So that's good to me. Very good. There's no class. Yeah, I mean, well, so yeah, in this statement, we said everyone. So what does this mean? Everyone in the world, you know, could be, um, and one person where, like in the class, we don't know. Um, and again, this everyone is not scoped. This everyone is not scoped. Um, so yeah, we have to make some assumptions here. And yeah, I mean, I think it's actually pretty normal to see this kind of thing in like a paper, for example. So I don't think anyone would say something as absurd as like this is true for any number when they really just mean the integers. Um, but I know actually I think for example if someone said for any value of n in a paper where we're talking about n is the size of a graph, nobody would be silly enough to assume that n could equal 2.3, right? But we do kind of use this kind of context to assume what set a variable belongs to. So yeah, yeah, you're technically right. I didn't say that they're in the class, but yeah, you should assume here. Okay. Um, what is the next one? Everyone considers everyone a friend. Oh, that's so nice. Joy. Okay. Uh, I have one answer here, which doesn't make sense, and I don't want to poke fun at this person, but this is actually a really good example of a mistake that happens sometimes. So it's this one, and uh, so again, CS majors have a slight advantage here, and the weird thing that's happening here is that there's a y here, and we don't know what this variable is. So you can imagine that if your compiler is looking at this and it sees y is being used actually in this function. It sees y, so it's just going to yell at you that it has no clue where this is from. And the same is true in math. Anytime you use a variable, it has to have been instantiated somewhere. and it can only be instantiated universally or existentially. So um, this y has to come from a for all or a there exists. So let me just pull up another. Okay. Here. So we have this. This answer is correct. So we see everyone. So we're making a statement about everyone. So I would do this. And then I see, okay, after I make the everyone, then they consider everyone a friend. And then the rest seems fine. And so we have another interesting answer, which is also correct. This one. The typo, but that's fine. And so this person has written both directions here, but it turns out that you don't need it. You don't need both directions because, so basically imagine that what we're doing is we're picking every possible value of x and every possible value of y, and we're plugging it into whatever we have as a conclusion here. So when I pick x and y here, right, I'll get this to be true. But later on, y will be here and x will be here because we're going through every possible value. And so you'll get y comma x as a result. You'll end up hitting this, I guess you can say, later on. So it's not actually necessary to say it. So it's kind of like looping through all pairs if you were to do something in Python like and you wouldn't have to if you printed every pair, right? X, y. You don't need to print yx in order to get every single pair because you're gonna get yx later on. And there was one more answer. Okay, there's some discussion about. Okay, for all x in C, f of x, x is appropriate. No, so that would be a different statement that says that every person considers themselves a friend. So is it necessary to introduce x not equal to y? Sometimes it depends on what you mean. So good that you're noticing that some weird stuff can happen sometimes when you talk about someone liking themselves as a friend. But we're saying everyone considers quite literally everyone. So in this case, that technically means you consider yourself a friend, right? So yes, we're all narcs. Right. I wanted to yeah here. So this is what I have in the notes actually. No worries if you just took it from there. But this is like a shorthand way of combining like this. So I lied. Sorry, this. So I lied when I said there's exactly one way to use a universal quantifier. This is the other way. You can combine things as long as they come from the same exact set. So x and y come from the same exact set, and also they use the same exact quantifier. So we're allowed to do this basically because this statement and this statement commutes. So I could have written for all y comma x in C, and it's also the same exact thing. There's no difference between them. Okay, so thank you all for supplying answers. That was instructive. Yeah, now it matters, or maybe let's not spoil this. Okay, so this one is tricky. Everyone has at least two people who they consider should be friends. Is Paul drinking Diet Coke? Yeah, Paul, if you drink Diet Coke a lot, it's better to use a straw because it's pretty acidic. It could hurt your teeth.
Thank you.
Hi, Tom. Thanks for joining us. We're all about to play Fortnite pretty soon. So just add me on Epic Games and we'll get started soon. Okay, so everyone has kind of probably understood the quandary here. Um, right. So we have an attempt, and thank you for that. Um, so the quandary here is how do you make it so you get two people? So here's the attempt. So good for all x and c. I totally agree. We're talking about everyone has. Another attempt. Throw it in here. So we're talking about everyone has, and we're saying at least two. Okay. So we're going to try and figure out how we can talk about two people because we're only used to at least one. So the guess here is, okay, we have A and B, which are also classmates, and X likes A as a friend, and X likes B as a friend. The problem is, this doesn't quite work, and Paul has posted the correction. Thank you, Paul. The problem is, and here's the counterexample. Well, you can have actually a really silly counterexample. So there's one person. So one considers one a friend. And so now, how can I make this statement true? Well, it's simply just true. So we pick x equals 1. We pick a and b equals 1. And it's true that 1 is a friend of 1 and 1 is a friend of 1. So you do need that a is not equal to b. So I will take this and put Paul's correction on there. X. And we'll use any q. Any q in latex is not equal. And now here we have an example of abusive notation. So probably what was meant here is that x considers y a friend and x considers z a friend. But obviously this function f is not defined like this, right? So function is a very concrete object. And you usually can't really extend this in certain ways unless like there's a some kind of well-established convention for doing this kind of thing. And generally, increasing the number of arguments, I don't think there's any conventions I'm aware of. So you should try to avoid this kind of thing. And also, it suffers from the lack of the y not equal to z. Yeah, so this is how you do it. So you can see all of a sudden, my call ends in 10 minutes? Are you kidding me? Okay, that's fucked up, guys. Okay. Okay, let's see if we can finish in 10 minutes, but so the term for this is signature in CS, but like can two distinct functions exist with the same name but different inputs? Uh don't do that. So again, so like if you have a compiler, right, it's very strict, right? It has things that work and things that don't work. When you're writing math, it is partly an art. And you can do bad things, but you shouldn't do bad things because they're bad. So don't do that. Um, is there any convention for defining variables? It's a very vague question. If you can make it more precise, we can talk about it. I'm just gonna make a new meeting now before like I forget because it's just kind of looming over my head. So is this so stupid? Oh, I'm in 2 meetings now. That's great. Well, I'm gonna leave this one. Goodbye. We have an imposter. Uh, so Google is warning me that one person who tried to join isn't who they claim they are, possibly. Um, you guys can figure that out. Yeah, yeah, I guess you could say there's an imposter among, anyways. Let me share my screen again. Screen, blah, blah, blah. Okay, so Right. So this is an interesting question because we've actually expressed something pretty interesting in a non-trivial way. We can talk about at least two people. We could also talk about at least three people, and then all of a sudden it gets really freaking annoying because then you would have to put a third variable, and then you'd have to say f of x a, f of x b, f of x c, a not equal to b, a not equal to c, b not equal to c. So it gets terrible when I keep increasing this number too. Um, but yeah, you can just replace two with whatever number you want. Okay, so let's move along. Oh, negation. How fun. Oh, I should put this back. Okay, so we still have some more nice tools in our logic tool belt. So negation. So it flips the truthiness of a proposition. You can stick it on just about anything. And you write it by putting it directly in front of your proposition. In LaTeX, it's \L naught. So we have to learn how to negate anything that we might come across. So we have to figure out how they interact with quantifiers. So this is really interesting. So right. So if we negate this nice for all statement we have here, then we get an existential statement all of a sudden. So look, so we had a not for all x in big X, f of x, and its negation is going to be there exists an x in big X such that not f of x. I'll just pause for a moment. You can think about what I just said. So we can kind of think of this as oh god, I okay. So in math we have a tendency to talk of elements as guys. So we might talk about good guys and bad guys, and good guys are the things that have the property we're interested in. And then I remembered Among Us and thought of using imposters and crewmates, but that's probably not going to be helpful for understanding, so I'm not going to do that. Um, anyways, so if we think about the basic statement here, for all x in big X, f of x, this is saying everything in our set is good. Now, if we look at the negation, we're saying it's not true that everything in the set is good. So if we're saying it's not true that everything is good, then that is the same exact thing as saying there's at least one guy which isn't good. Right, so you kind of have this dual notion here where either everything is good or at least one thing is bad. Right? Either the number of bad things is zero or it's more than zero. And now the same thing kind of happens when you negate an existential quantifier. So now let's think about what we're saying. We're saying here there exists at least one thing which is good. Now when we negate it, we say, okay, it's not true that there is so here when we negate it, we say it's not true that there is at least one thing which is good. It's not true that there is at least one thing which is good. So in that case, then everything is bad. Okay, so these are dual notions, and you can kind of see that if you think of this as like kind of an equation, you just kind of move the negation around. If you think of it as a minus sign, you shouldn't really think of this as a minus sign, but it does double negation does cancel with itself, and we'll see that a little bit later. Okay. So I don't know why I chose to talk about negation of quantifiers first. It would make a little bit more sense to do it with conjunctions and disjunctions, but okay. Let's now talk about this. So let's negate a disjunction. So if you recall, a disjunction is or, it's logical or. So this statement is saying at least one of P or Q is true. And now if I negate that, then it's the case that neither P nor Q is true. So neither P and not Q. Okay. So I'm kind of just appealing to your intuition here. But if you sat down and did something called a truth table, then you would be able to prove this very concretely. It's just really, really ugly. So if you take, for example, CS205, Street 1, they will make you do these really ugly truth tables, and I think they're a total waste of time. I think also 300 they might make you do them, but um, they don't teach you anything. But what you should do is get used to these identities, and part of the homework will be kind of just going over these kinds of things so you get used to it. Okay. Let's also negate a conjunction. I think this is backwards. Above I introduced conjunction first, but whatever. Okay, so P and Q is saying P has to be true and Q has to be true. But now I'm negating it, so that's not the case. So maybe P is not true, or maybe Q is not true. Okay. And this triple equal sign is backslash equiv. It's used specifically for like when you're doing this shorthand notation with logical stuff. So if you're just like chugging propositional variables around, you would use a triple equal sign. So these two rules for negating conjunction and disjunction, these are known as De Morgan's laws. And there's other variations on De Morgan's laws, and we'll see that later on in lecture 2 and maybe again somewhere else. And there is a really nice general rule for negating things. Flip literally everything. It's like the most relaxing thing in the world. Take everything and flip it. So let's take this. Let's go back to Gates code. Oh, it pastes like that. That's great. Okay. So let's do this. So I take exists. Okay, but I don't want to like so I take everything and I flip it, so exists becomes for all. I can't flip these things, they don't have dual notions. For all becomes exists. And then I flip this thing, so I just put a negation on top of it. Looks good to everyone? Great. Well, I didn't wait long enough to confirm that, but I'm sure this isn't. So in this example, we just have this, and again, I just look at everything and I just negate it. So for all, it becomes exists. Exists becomes for all. I just negate that. Okay. More examples. Okay. This is gonna use De Morgan's law. So let's actually think a little bit for this one. Let's replace it with latex so you guys get a little bit of practice with this. For all in this y comma z in here, yeah, land. How did that happen? 6. Okay. Okay, good. So let's start negating this guy. So for all becomes exists. Exists becomes for all. And so let's just be careful when we see this kind of thing. So let's think about it. So this normally looks like exists y and c, such that there exists z and c. And if I negate both of those independently, I would get for all y and c, and then for all z and c, and I could combine those. So it is valid to just directly do this. And then now we need to negate this entire thing. So now we need to be a little bit careful. So we have this big statement. So when we're negating conjunction, right? So logical and, we're negating conjunction. So if we go back to our notes, when we negated the conjunction here, the conjunction became a disjunction, and each individual variable became its negated form. So we're just going to do the same thing. It does generalize to however many variables you want. I'm not going to prove that for you, but you could write it down by basically making q equal to the and of two other variables. And then when you write it as this, then you can sub in those two variables again and then negate that, and you'll get what I'm talking about. But anyways, we're just gonna assume that for now. So I take everything I see here and I basically just flip it. So I get L naught f of xy. I have a land. Land becomes logical and becomes logical or. And then I have f of xc. So L naught of c. I have a land becomes logical or. And then, so I'm not going to put a logical not here because my statement is y not equal to z. So if I negate y not equal to z, I just get y equal to z. Okay, and it's like, it's relaxing. You can just take every single symbol, and if you can flip it, then you do. Okay, any questions on how negation works? I know I kind of went a while without pausing. How about this? So I feel like maybe if someone's typing out a question, it might take some time to do that. So if you do have a question, just raise your hand so I know that you're typing. Okay, so no questions. Everyone is now a master on negation. Good job, everyone. Let's continue. Okay, so yes, nice job, everyone. What do we got left? Just implications. Great. Okay, so the reason I do implications after negation is because implications are not actually a new thing. You can write an implication by just using the tools we've learned before. So implication is kind of like syntactic sugar. You don't need it, but it's very, very critical to how we write logic. So you absolutely have to learn what this is doing. So an implication P implies Q is what we would say here is true. As long as, and bear with me with the sentence, it's true as long as Q is true whenever P is true. So this implication, I'll just repeat myself, is true as long as if we have the first part, then the second part must also follow. So I like to think of this as a promise. It's like a challenge. So my implication can be kind of this nonsensical statement, and I can be really ballsy, and I can say whatever. And my claim is as long as you give me the first part, I'll give you the second. But if you can't give me the first part, then it doesn't matter if I can give you the rest, because I haven't broken my promise by stating this. So let me see. Oh yeah. So just side note. Always use a double arrow if you're like writing down something physically, or you're just using LaTeX. If you use a single arrow, this is like actually a completely different notion. So just be careful of that. Okay. Right. So let's go back to this silly thing I was talking about. So I'm being very confident saying, if you give me the first part, I'll give you the second part. So someone can only call my bluff if they give me the first part and yet I fail to produce the result, right? If someone gives me P and I'm not able to give you Q, then my implication was wrong. Then I broke my promise, right? So the implication is false precisely if we have this. P is true and Q is false. So the negation of P implies Q is exactly this. Does that make sense? You can only show if someone broke the promise if you found that the initial part was fulfilled, but the result wasn't. Okay. So now, by using the negation of an implication, we can actually write it in terms of our regular logical tools. So now let's negate both sides. Let's recall that double negations just cancel out. And so I negate this. I use De Morgan. So if you just follow along, I negate this. I get not P. I negate this. I get or. I negate not Q. And I get just regular Q. So what we see here is that P implies Q is logically equivalent to not P or Q. So my implication is true if the hypothesis, the first part, is just never true, or if the result is always true. So this tends to trip people up a lot, because this is not really how we think of implications when we think of this logical implications in real life. So what the heck? I don't have any examples. So I mean, here's a silly example where the implication is true because the not P part is true. So here's my implication. If Obama is the president, then I will give you $1 billion. So obviously Q is not going to be true because I don't have $1 billion, but not P is true because Obama is not the president. Similarly, I could say dogs are small implies the sky is blue. And the initial value doesn't matter because the sky is blue, so since Q is true, the implication is true. Okay, I'm seeing people getting bored, so I'm just gonna move. But I just kind of overhammered this because I find that a lot of people get confused with this in learning logic. Okay, and finally we have just a little bit of vocabulary. This is nice to use in your proofs. So P is sufficient for Q if P implies Q. So it's easy to get these backwards. So P is sufficient for Q. So when I say sufficient, I'm saying this is enough for Q. So what I'm saying is that if I had P, then I would definitely have Q. So that just means P implies Q. And then here's kind of the confusing part. P is necessary for Q means actually Q implies P. So if P is necessary for Q, that means that if I had Q, then P must have been true because P was necessary for it to be true. Okay. So, and finally, if we say P is necessary and sufficient for Q, we can write sort of logical equivalence as this biconditional arrow, which I failed to put the LaTeX for, I'm sorry. I think it is left-right arrow. So here you would do capital L left and then lowercase r right, all one word. So yeah, so this is the same as logical equivalence. We just write it sometimes like this when we're working with theorems or something like that. Okay, that is the end of the lecture. Any questions? Yeah, it is like that. So the homework is due Monday at what was it, 5 p.m.? Wait, no. I had a weird thing where it was like between 3 and 5. Fortnite and Among Us. Yeah, please submit it by 3 if you can. So basically the point is that if graders try to go grade something and there's nothing left because someone didn't submit it in time, then homework is immediately due and then I won't take it anymore. And the reason for being so strict about it is basically because like graders are under a lot of pressure to get things back because there's basically no time to make sure you get the feedback so that you know what you're doing later on. Yeah, go ahead, Paul.
Oh, where do we submit the homework?
Oh, right, I forgot about that. I'll make a Google Classroom, or maybe Contron will make a Google Classroom. Okay, any other questions? No? Okay, cool. Thank you all for coming, and see you guys on Monday.
Thank you.
Thank you.
Good night, SDs.
Good night.